Hey, welcome everybody to physics this morning. This is one of my favorite days of the whole year because we're going to talk about the tug of war. So here's the opening question. Who wins the tug of war? Now, see in parentheses here it says rope does not slip through hands. So in other words, both teams have a firm grip on the rope and it never slips through that grip. Who wins the tug of war? The strongest, the heaviest, the one that pulls the hardest on the rope, or some other answer? Talk about it and get back to me. Okay, so who says A? Okay, nobody. Who says B? Okay, we got 3. Who says C? Okay, classically that is the answer that everyone says, including the authors of our book. But like Andrew said, it's probably D because why else would I have that up there? And that is the correct answer. D is the correct answer. The some other answer is the team that pushes hardest on the ground towards the other team parallel to the rope. Okay, so I'll explain that a little bit further. Now this is Newton's third law. So this law is the law that is the most misunderstood out of all the laws. Newton's third says this. Well, I think what Newton said maybe was, he probably said, you can't push or pull nothing. You can't push or pull nothing. Okay, you guys heard of Newton's third law in this way. Okay, so Newton's third law is not usually stated this way. This is the way I state it because it makes sense to me and it's easy. Newton's third law is more classically stated in the textbooks as for every action, there's an equal in magnitude but opposite in direction reaction. And then they go on to give some examples of if you hit the nail with a hammer, the nail is hitting the hammer just as hard as the hammer is hitting the nail and stuff like that. And then they kind of fail to go much further than that, especially in the high school books. But we will go further than that because College Board says that when we do the problems that we're going to do next, it exemplifies Newton's third law as long as you look at it as you can't push or pull nothing. So let's do this. Put your hand up to your neighbor and have your neighbor push as hard as they can on your hand. Okay, so now did you feel that force? You felt that force, right? Okay, so let me ask you this. Now what I want you to do is, if you're me, I'm the one holding, and the other one's pushing hard. Go like this, and see if they can push that hard again. Come on, just push that hard. Okay, it doesn't work. Okay, so the second time you push the hand and the person pulled their hand away, you just couldn't push that hard. Because there was nothing there to push. That's what Newton said. He said, it's impossible to force onto something that doesn't force back with the exact same force. Because you can't push nothing. You can't push something that's not there. And that's why letter D is the right answer. It's some other answer. And now to kind of explain that answer a little bit better, if we have our rope here and we have our team latched onto the rope, now keep in mind, if the rope slips between the hands, that's a different story. Because then the team that it didn't slip through actually did pull harder on the rope. But if it doesn't, which if you've seen many tug of wars, it usually doesn't, right? It's like there's a little flag here and it just kind of inches over, right? So what's happening is this guy is pulling on the rope with a force. This guy is pulling on a rope with that exact same force. Because all the rope does is translate that force to the other side, to the other end. That's what tension does. Right? And if you want to break it down, you could say that this guy's pulling on the rope and the rope was pulling back. But then in turn, the rope was pulling on that guy. And you could break it down a little bit further, but you don't really need to, because the rope is there. Okay, but now, if this guy pushes on the ground with the big force, what is the ground going to do to him? The ground has to push back with a big force because he can't push nothing. He can't push on the ground harder than the ground pushes on him. Because just like when you take your hand away, you can't push it if it's not there. Does that make sense? But this guy here is pushing on the ground less, and now you can see that these poles up here are going to be equal to those poles, right? The poles up here are equal to these poles down there. They should be equal in length because that would be the hardest that this guy could push on the rope or pull on the rope, because that's how hard he's pulling on the ground. Well, this guy's pushing on the ground much harder, so therefore this whole system then, so really the tug of war is like one system or one box. The whole box then ends up moving in the direction of whoever's pushing hardest on the ground, parallel to the rope, in the direction opposite, or in the direction of the team. So this would be the force of the person, and then this one's the force of the ground. Does that make sense? Okay, so what does that have to do with anything? Well, it has to do with what we're going to be dealing with today. It's called pulleys. Okay, and so this is to exemplify this Newton's third law, the tug-of-war system. Okay, so if I have a pulley, and all of our pulleys are going to be massless and frictionless. Okay, and we have a rope that has a 2 kilogram mass, and on the other end, it has a 1 kilogram mass. Okay, so is this thing going to move? It's going to accelerate even, right? Okay. And if you think about it, now we're going to show the free body diagram on each one. Well, maybe I won't go so far as a free body diagram, but the Earth is pulling on this with 20 newtons. Do you agree? And the Earth is pulling on this with 10 newtons. Okay, so which one's going to win the tug of war? The 20 newton, right? So the first thing you want to do is mark in your acceleration of the system. Okay? And now just for fun, just so you know, I'm going to label this side T1 and this side T2, but those two have to be the same tension. But in order for us to solve the problems in the manner that exemplifies Newton's third law, we need to label them as two different tensions, but you have to know in your head that they're the same tension. So what you end up doing is describing these tensions in two different ways. So as you work through this problem, you kind of put a slash here. Oops. A slash here. Thinking that on one side of the slash is one problem, or one side of the problem, and the other side is the other. And so the slash then is kind of the equal sign. Okay? And we're going to say that T1 equals T2 because it's only one rope, there can only be one tension. Okay, so now let's describe tension 1. The first thing that you always have to do is include gravity because that is always there. So T1 is going to have the force of gravity on the 2 kilogram mass. But what else is there going to be? Or in other words, what else isn't there going to be? Or in other words, take your book and raise it up in your hand for a second. Okay, so I need to draw a picture here. I got this book in my hand. And if I take the book and I raise it quickly above my head and I accelerate that book, I can feel a change in the force that my hand applies to the book. What happens to that force? It gets bigger or smaller? It gets bigger, right? Because I need to have a bigger force. So if this is the force of gravity, this would be the force that caused it to accelerate upwards, and I can feel that in my hand. But now if I take it the other way, and I lower the book, then what happens to the force? it decreases, right? Because if this is the force of gravity and this is the force of my hand, then the thing is going to accelerate downwards, and it feels lighter, right? So when you catch a ball coming really fast, you kind of go with the ball because it decreases the force that you have to apply. Do you agree? You really have to understand this. Okay, so how is that going to work into our math? Well, on this side, tension 1, we can say we're going to have the force of gravity, and is it going to be more or less than that? We're accelerating in this direction, which means, is it going to be more or less? It's going to be less, right? That's just like when you put your hand down, it was less. So we have to do that, show that by subtracting the mass of the 2 kilogram times the acceleration of the system. Keep in mind, force is a mass times acceleration. So if we have this mass times acceleration, that's an amount of force that we're decreasing the tension on this side by. Any questions about that? Okay, so now if we look at T2, we have to start out with the force of gravity all the time, Force of gravity of the 10 kilogram. Now, is that 10 kilogram going to be pulled up or it's going to go up, right? Which means, what about the force? Is it going to be greater than gravity or less than?
It's 1 kilogram.
Oh, I'm sorry. Yeah, it's 1 kilogram. Thank you very much. 1 kilogram. Okay, so are we going to add more force to that or less force? Well, if you're pulling something upwards, you're going to add to it, right? So we're describing the tension, and we're describing how tight this rope is. Well, it's not just 10 newtons. It's got to be tighter than that because it's going to accelerate that 10 newton mass upwards. So that's going to be then plus mass of the 1 kilogram times acceleration of the system. Okay, so now we have equation for tension from the perspective of the left side and the right side. These are both valid equations for the tension, which we can use later when we're trying to figure out tension. So really what we have to do now is solve for the acceleration of the system, right? Because then we can find the tension from either equation. So now we start plugging the numbers in. And the force of gravity on the 2 kilogram mass is 20 newtons, minus, we have 2 kilograms times acceleration of the system, and then we have 10 newtons, plus 1 kilogram times acceleration of the system. Okay? So now we'll have to do some algebra and determine what our acceleration of the system is. Our next step would be 3AS is equal to 10 newtons, or acceleration of the system is 3.33 meters per second squared. Okay? So the hard part's done. And now we can take this acceleration of the system and plug it into either one of the equations and solve for tension. So we'll plug it into that first one. Tension is equal to 20, which is this right here, minus 2AS, which is 3.33, 13.33 newtons. If I did my math correctly, please check that. Okay, we're going to go through a couple more examples. They're going to be just a little bit faster than that. So keep in mind that that will be 2 kilograms, this will be 3 kilograms, this will be 4 kilograms. This time we're actually going to have different T's. T1 and T2 will be equal to each other, but T3 is not equal to T1 or T2 because T3 is only hanging on to the 3 kilogram mass. But we can look right now and we can figure out that the acceleration of the system is in this direction. right? Because 50 on the left, 40 on the right, it's going to accelerate to the left. So we can say still T1 is equal to T2. And in this case, T1 is 50 newtons, because it's both the 2 and the 3 that are being held by that rope. So it's 50 newtons minus 5 AS, and it's minus because it's going to be falling down, so this rope doesn't have to pull as hard as 50 newtons. It's going with the masses. And then T2 is going to be 40 newtons, because that's the force of gravity on that, and that'll be plus 4 AS, because it's going to be yanked up. So it's going to be forced upon harder than its gravity to accelerate it upwards. Okay, so now we just simply solve for this, and 9 AS then is equal to 10 newtons. So acceleration of the system is 1.11 meters per second squared, if I did my math correctly. So now that we have the acceleration of the system, we can solve for, we know that T1 is equal to T2, and we can just say T1 is 50 newtons minus 5 times 1.11. So T1 and T2 then are equal to 44.45 or something close to that. What is the actual number? Okay, so you can do that, right? And now we just have to write an equation for T3. So T3 is equal to 30, because that's how much force the Earth is pulling on that mass, minus 3 AS. So T3 then becomes 30 minus 3 times 1.11. T3 is 26.67, if I did my math correctly. Okay, one more. Okay, so we'll have a ramp this time, and we'll have this situation, okay? So we'll call this T1, call this T2. Okay, so this time we don't have the force of gravity, because that's not in line with the rope. But what we do have is the force of gravity down the ramp, which is sine theta mg. We'll give this 2 kilograms. We'll say this is 1 kilogram. We'll say this is 30 degrees. So the first thing we have to do is figure out who wins the tug of war. So this is a little bit harder than before. So we'll say right here that T1 is equal to T2, and we'll start plugging in. So T1 would be sine of 30 times 20, okay? And T2 is 10 newtons. Those are the 2 components that are forcing on the rope, because the Earth is forcing on those 2 pieces. So what's bigger, the sine of 30 times 20 or 10? Ooh, it's the same, so that means they're not going anywhere. Right, so we're going to start this problem over. And we're going to say that this is not 1 kilogram. We're going to say it's 1.5 kilograms. And so that changes the tension on this side to 15 newtons, or the weights to 15 newtons. Now which one's going to win? Now we can say that the acceleration is going to go this way. Okay? So the question was, how are these equal and they're still accelerating? Well, so Newton's third law says that this mass can't pull any harder on the rope than this mass pulls in the opposite direction. It's impossible, because you can't pull or push nothing. So that's why we can split this up, and we can use our equal sign, saying that really when we're saying T1 is equal to T2, even though we know it's the same tension, we're saying that this block is pulling on the rope just as hard as this block is pulling on the rope, because it's impossible to do otherwise. So that's the whole idea of this being Newton's third law. Thanks for bringing that up, Morgan. Okay. So, now that I've changed the numbers so we can actually have an acceleration, because sine of 30 times 20 is 10, right? And this is 50. Now we can put in our plus or minus acceleration of the system. So in this case, T1 is going to be pulled harder than the force down the ramp, right? Because it's going to be accelerated. This is going to be accelerated, so you need to force on it harder than the force. So I'm going to put then a plus 2AS. Any questions about that? Plus 2AS. This one's going to be minus 1.5 AS because it's going to be falling with the system, so the rope doesn't have to pull as much as 15 newtons. Does that make sense? Okay, so now let's just back down to what we do. So we have 3.5 AS is equal to 5 newtons. So acceleration of the system is 1.43 meters per second squared. Okay, that's our acceleration of the system. That's the hard part. Now we can fill into either, let's use this side to figure out the actual tension. Okay, so we'll say that tension is equal to 15 minus 1.5 times 1.43. So tension is 12.86 newtons. Okay, well, hopefully that helps you do your math, and hopefully it helps you really get Newton's third law.